I'm going to talk about a bio-inspired optical compass for robotic applications. This work was carried out in Marseille, France, both at the Institute of Movement Sciences (ISM) by the Biorobotic Department and at the Institute of Materials, Microelectronics and Nanosciences in Provence (IM2NP) by the Lumen PV department. I will start by describing ants living in the desert as a model for implementing bio-inspired navigational strategies. Then I will explain the polarized skylights coming from the sky dome, especially in the ultraviolet range. Next, I will talk about the design of an ant-based optical compass implemented on board a hexapod robot called AntBot. Finally, I will end by proposing an inexpensive version of our optical compass for industrial purposes. Then I will conclude and make some future projects. Desert ants are known to robustly estimate their position relative to the nest while foraging for food, which is a genuine tour de force and a great source of inspiration for designing navigation systems working without GPS or any global navigation satellite systems GNSS. Desert ants use a powerful navigational tool termed path integration, which is a kind of an invisible Ariane's thread when returning to the nest using the shortest possible route, a straight line, even in featureless or unfamiliar terrains. By integrating a directional compass and distance information, the ants obtain a vector which leads them home. But how can these animals estimate their heading? To navigate autonomously in the desert and to home, ants use idiometric cues, ventral optic flow and strike counting, and heading cues based on the polarized light coming from the sky dome, and also the sun's positions. Ants also use visual guidance strategies based on snapshot matching between current view and familiar views to get back home. Finally, they can use olfactions in the neighborhood of the nest. In this study, we will focus on heading detections based on polarized light in the ultraviolet range. According to the Rayleigh scattering model, the sun's light coming from the sky is polarized, which means that this light can be characterized by its degree of polarization, DOPL, and its angle of polarization, AOP. The degree of polarization is stronger not only at 90 degrees from the sun, but also at low wavelength, especially in the UV range. According to the Rayleigh model, the pattern of the polarized light from the sky can be seen as concentric circles centered around the sun, in which we can detect a silent feature represented here by a black line. Here it is clearly shown that the percentage of scattering of direct sunlight is larger in the UV range than in the visible range. In addition, it has been shown that the degree of polarization is also higher in the UV range. Barta and Horvath in 2004 gave an explanation of the UV range preference in insects by showing that the UV range is strongly resilient to cloud coverage. Finally, this panoramic view of the sky, here in the visible range, showed that the sky dome can provide a silent cue for estimating the heading of animals and potentially autonomous robots. On the left, we can see the AntBot, which is a hexapod robot endowed with several visual sensors mimicking the compound eye of an ant. AntBot is fitted with an optical sensor looking downward to optically estimate its travel distance. AntBot is also fitted with a 2-pixel celestial compass that detects the state of polarization of the skylight in the UV range. This compass provides an optical aiding while navigating outdoors, with excellent performances regardless of the environmental conditions. By combining distance measurement and heading, we have shown that AntBot is able to perform path integration to home with a great accuracy, about 0.5% of the travel distance. To process the visual signals provided by our optical compass, we took our inspiration from what we know to be in the pole neuron of a cricket's brain. It was suggested by Labart and colleagues that the visual processing in the cricket's brain consists of implementing the log ratio of the two output signals from two adjacent photoreceptors. These two photoreceptors have polarizing filters called microvilli oriented perpendicularly to each other. Such a bio-inspired approach requires extremely low computational resources to find the heading. By rotating the two polarizing filters placed on the top of the two photodetectors, we obtain two signals following the Malus law shift by 90 degrees due to the initial orientation of the pair of polarizing filters, as previously described. By taking the mean and the max values of the log ratio of these two visual signals, we can show that it is possible to measure the heading with a great accuracy, about 0.4 degree. We compared our method for estimating the heading, called the AntBot method, to 4 previous methods. Our AntBot method achieved the best accuracy in all weather conditions. In addition, we tested our compass under foliage and on board a vehicle fixed onto the roof of a car, and its performance remained constant. In conclusion, the AntBot method had 3 major advantages over existing solutions in optical heading detection. Firstly, an accuracy from 0.5 degree to 0.6 degree. Secondly, resiliency even in poor weather or under foliage. Thirdly, no mathematical ambiguity. It does not require an arctangent function to compute the heading. Here there is a description of MiMiCOMPAS electronics in A. First, we use two UV LEDs operating as detectors and topped by a pair of orthogonal polarizing filters. The photoconductors measured by LEDs are directly connected to a logarithmic amplifier LOG104, and the output is amplified by an amplifier ROP-TL3472. This solution is completely static, insensitive of the time of the day and cloud cover, and relatively fast in the processing stages. This solution must be extended in B with sensors positioned on a 1 degree circular crown to cover all polarization direction from 0 degree to 90 degrees. This slide shows some features of the sensors used in the AntBot and MiMiCOMPAS projects. Firstly, the economic aspect of optical sensors and filters. The financial gain of the MiMiCOMPAS solution is very high, more than a factor 100 to build 140 optical units. As regards metrological characteristics, the optical properties are equivalent. On the other hand, the materials that make up the sensors are different. The optical characteristics of the 4 selected polarizing filters are obtained by transmission spectrometry measurements. Apart from the 3D lens UV cut filter, which blocks the low wavelength, thus is unnecessary. The characteristics of the other three filters are equivalent, but the cost of the 3D lens non-UV cut filter is significantly lower. Here we can see the spectral sensitivities of the AntBot and MiMiCOMPAS detectors coupled to their respective polarizing filter. The wavelength selectivity is equivalent to a maximum of 343 nanometers for the AntBot celestial compass and 380 nanometers for the MiMiCOMPAS celestial compass. This difference is explained by the different nature of the semiconductor materials used in the two photodetectors. The spectral coverage of the MiMiCOMPAS sensor covers the UVE and violet domains, which allow us to save money. Some details of the experimental measuring bench are represented by these pictures. The source used emits at 395 nanometers. The beam is polarized by the 3D lens filters mounted on a 1 degree resolution goniometers. The light intensity arriving at the pair of the UV LEDs is measured by a Voltzcraft UV meter. With regards to the degree of polarization DOPL, we present here experimental measurements obtained by the works of Eshelman and Shaw. The variation of the degree of polarization for the latitude concerned here, close to that of Marseille, ranges from a few percent to 60%. In our experimental bench, we are only able to generate a constant degree of polarization of about 20%, which is similar to the one in Marseille during the time. This figure shows three series of measurements obtained for different light intensities. The rotation step of the polarizing filters is equal to 5 degrees, and the plots show the evolution of the output of the LOG-104 amplifiers. The plots are similar even at low UV levels because the dynamic range of the LOG-104 is 7.5 decades. The detection of the minimum and maximum values allows the robot to find the angle of polarization. In order to compare experimental measurements with simulated ones, we performed some electronic simulations using LTSPI software. We can see here that the simulation results agree with those of the previous experiments. The two plots represent simulated curves for 6 different angles of polarization. The position of the extrema allows us to calculate the initial direction. Consequently, the phase shift from the Malus law allows us to estimate the robot's heading. In conclusion, MiMiCOMPAS Celestial Compass was designed to provide a low-cost solution for robotic services, for instance, autonomous delivery services. Secondly, MiMiCOMPAS is more than 100 times less expensive than AntBot and does not need any mechanical rotative systems to scan the sky dome. Thirdly, MiMiCOMPAS is a static version of AntBot Compass that can work more than 40 times faster with a similar accuracy of 0.5 degree, 0.6 degree. Finally, the integration and miniaturization of MiMiCOMPAS is underway. Thank you for your attention.